Hi everyone, welcome back to the course manufacturing process. In this part we are going to discuss about forces acting on a chip. As you could see here, whenever a tool with a rake angle alpha cuts a material, the frictional force F and the shearing force Fs are acting on the workpiece as shown here. So the deformed chip, as you see here, deformed chip is in compression against the face of the tool, which produces a frictional force F, and the force that causes the shear deformation to occur across the shear plane Fs. These are the two main forces, Fs and F. Because of this, there is Fc, which is the cutting force acting in the direction of cutting. So there is a force called N, which is the normal force to the friction. There is a force called Fn, which is the normal force to the shear force. The vector addition of F and N is R, the resultant is R, and the vector addition of Fs and Fn is R dash. In order to balance the cutting operation, R dash must be equal to R. They should be opposite to each other and they should be collinear. The shear plane angle is represented as phi, and the angle, the rake angle, the angle of the tool is represented as alpha. So the friction force is represented by F. Normal to the friction force is N. The resultant is R. The shearing force is Fs, across which the shearing takes place, and the normal force to shearing is Fn, and the resultant is R dash. In order to balance the operation, R dash must be equal to R, must be collinear and opposite to each other. Now, the coefficient of friction can be represented as mu, which is equal to force F divided by N. Frictional force F divided by normal to the friction force will give you the coefficient of friction. So this coefficient of friction can also be written as tan beta, whereas beta is called the friction angle, or beta is the angle between the resultant and normal to the friction force. So beta is the angle between the normal to the resultant. So we call it as friction angle. So mu is equal to, or coefficient of friction is equal to tan friction angle or tan beta. Shear stress can be calculated as shear force divided by shear area. Shear area will not be the normal area because there is some deformation takes place to the workpiece. So it will be T naught W divided by sine phi. T naught is the initial thickness, W is the width, and phi is the shear plane angle. So cutting force and thrust force. So as I explained before, cutting force is the force in the direction of cutting. Force in the direction of cutting, we call it as cutting force Fc, represented by Fc. And thrust force, this is needed. Thrust force is the force needed to keep the tool in workpiece in a direction perpendicular to the workpiece. So thrust force is a force needed to keep the tool in workpiece in a direction perpendicular to the workpiece. So the resultant of Fc, the cutting force, and thrust force will be R double dash as shown here. So what we can detect, what we can calculate. One important parameter we need to understand is we will not be able to measure the frictional force, the normal to frictional force, the shear force, or the normal to the shear force. We can use certain equations to calculate them, but we cannot measure it. But we can measure the cutting force and the thrust force. So using the cutting force and thrust force measured, we can calculate the frictional force, normal to frictional force, shear force, and normal to shear force. So what is the frictional force? Frictional force equal to Fc sine alpha plus Ft cos alpha. Alpha is a rake angle. Fc is the cutting force and Ft is the thrust force. The normal to the frictional force is Fc cos alpha minus Ft sin alpha. Shear force is Fc cos phi minus Ft sin phi. Fc is cutting force, Ft is thrust force, phi is the shear plane angle. Similarly, Fn, the normal to the shear force is Fc sin phi plus Ft cos phi. So these are the mechanics of cutting, or the different processes or different forces acting in a cutting process. As you can see here, frictional force to shear force. All these forces can be represented by in a force diagram shown here. Ft, Fc, all are shown here. The corresponding angles also given. We can find the resultant from this diagram. Now, Merchant equation. What Merchant equation indicates? The relationship between shear plane angle, the rake angle of the tool, and the friction angle. That is called Merchant equation. It is equal to, so shear plane angle is equal to 45 plus alpha over 2 minus beta over 2. So this is derived by a Merchant. That's why this equation is known as Merchant equation. Now, what is the Merchant equation? What is the importance of Merchant equation? So Merchant equation shows the shear plane angle phi will be higher if alpha is increased and beta is decreased. If alpha, the rake angle of the tool, is increased and beta, the friction angle, is decreased, then phi can be increased. Then what is the effect of phi? As you can see here, the effect of phi. What is the effect of phi? So as you decrease, you see here, as you decrease phi, see the phi, the angle, higher phi with, you see here, as the phi is high or higher phi value, there will be a very small shearing area. So shearing area less means shearing force less, shearing power less, or temperature less, etc. So as phi shearing angle increases, shearing area will be less, hence shearing force will be less, power and cutting temperature will be less. But see here what happens, you increased alpha, you increased the rake angle. As per this equation, you increased alpha, you increased phi. As you increase phi, the area will be less, force power can be reduced. But you decreased alpha, alpha is very less, so phi will be less. As phi less, you mean um, uh, we require more area, shearing area. We require more shearing area means we require more shearing force and more shearing power. So this is the importance of Merchant equation in metal cutting process. Similarly, we can calculate Fc, the cutting force, using shear force, cosine friction angle minus rake angle divided by cos phi plus beta minus alpha, and thrust angle equal to shear force times sine beta minus alpha divided by cos phi plus beta minus alpha. This already been discussed. So how to calculate power of cutting? Any machine tool, whenever we operate, our aim is to find what is the power, how much power we needed to cut this. So the power required is equal to force times velocity, cutting force times velocity. Cutting force is Fc, V is velocity, cutting speed. So the real cutting power can be calculated by dividing it with efficiency E. So PC over E is the gross power required. So the unit power can be calculated as a ratio of power required for cutting to the material removal rate. So power required to remove certain amount of material, this is called the unit power. So unit power is the ratio of power required for cutting to the material removal rate. So another term used is specific energy U, which is equal to the power required. This is the thing we have been used. It can also be told as unit power, either unit power or specific energy. We calculate it as power, which is FCV, cutting force times cutting speed, divided by the material removal rate, which is VT0 times W. So what is cutting temperature? Cutting temperature is the temperature produced during cutting, or while cutting, the temperature of the tool increases. So whatever energy you are supplying through the tool, 98% of the energy will be converted into heat. And the 2% of energy will be stored as elastic energy in the chip itself. So this 98% of heat energy, it will increase the temperature. So these cutting temperatures are very important. So you have to cool the tool by using suitable lubricants. So as the cutting temperature increases, it reduces the life of the tool. It produces hazards, safety hazards for the operator because of hot chips. Can cause inaccuracies because the material will expand, thermal expansion takes place, hence inaccuracies also takes place. So cutting temperature need to be carefully dealt with. How to calculate cutting temperature? The equation derived by Nathan Cook shows cutting temperature is 0.4 specific energy divided by volumetric specific heat. Rho C is called volumetric specific heat times cutting speed V times T naught over K raised to 0.33. This experimental equation is developed by Nathan Cook. U is the specific energy, Rho C is the volumetric specific heat, the heat capacity of the material, V is the cutting speed, T naught is the initial thickness, and K is the thermal diffusibility of the material. Another experimental equation which is used or which is derived is given here, which is derived by Ken Trigger, that is temperature T is equal to K times V raised to M. K and M are constants. If we measure the tool chip temperature using thermocouples, tool chip temperature measured by thermocouple, and substitute in this equation T, the temperature equal to K, a constant, times V, the cutting speed raised to M. If we get K and M at different cutting conditions, we can understand the process and we can calculate, we can predict the cutting temperature of a machining operation. So thank you very much for listening. Thank you.